In previous lectures we've talked a lot about the position and orientation of objects in the world. In this lecture we're going to talk about the rate of change of position and the rate of change of orientation. We're going to talk about velocities. In this picture we can see a ball moving through the air, and before we can say anything meaningful about the velocity or position of the ball, we need to introduce a reference coordinate frame, and by now this is a familiar concept to us. Now I can talk about the velocity of the ball, and I describe that by this blue vector which I've labelled v. So v is the velocity vector, and that describes the direction and the magnitude of the motion, of the rate of change of position of the ball at this particular moment in time, the moment when this photograph was taken. Now velocity is a vector quantity. It's got three components defined with respect to the coordinate frame, and that is the rate of change of the x-coordinate, that's x dot, the rate of change of the y-coordinate, and the rate of change of the z-coordinate. Now we're going to consider the rather more complex motion of a frisbee flying through the air. And once again, before we can say anything meaningful about the position or velocity of this object, we need to define a reference coordinate frame. Now the frisbee has got a translational velocity. It's moving through the air from the person who threw it to the place where it's going to land. But the frisbee also spins, and we say that the frisbee has got an angular velocity, and that's denoted here by the red vector that I've called omega. And once again, the translational velocity v and the angular velocity omega change continually as the object is moving. So these vectors represent translational and angular velocity at the instant that this picture was taken. The angular velocity, that's the red vector here, has got a direction, and that is the axis about which the body is rotating at this particular instance in time. And the magnitude of this vector is the rate of rotation around that axis. If the object was spinning very quickly, then the angular velocity vector would be very long. Once again, the angular velocity vector has got three components, so we can take this red vector and we can describe components with respect to the x, y, and z axes of our reference coordinate frame. Now it's not just frisbees and balls that have got translational and rotational velocity. The end effector of a robot arm has a translational velocity and an angular velocity, and often we need to specify what these are and in fact command the robot joints so that we get the desired translational and angular velocity of the robot's end effector. Typically we stack the elements of the translational velocity, the elements Vx, Vy, and Vz, and the elements of the angular velocity, omega x, omega y, and omega z, into one vector that's 6 elements long, and we refer to this as the spatial velocity or the twist of the object. We use the Greek letter nu, which looks a bit like a v, to denote this special quantity, this spatial velocity or twist, which has got 6 elements. It's a 6-element vector.